faulty battery can cause a serious fire. 208. Faulty chargers can affect the safety of the battery because they can destroy the battery's protection circuit. While charging at temperatures below 0 degrees Celsius, the negative electrode of the cells gets plated with pure lithium, which can compromise the safety of the whole pack. Short-circuiting a battery will cause the cell to overheat and possibly to catch fire. 216. Smoke from thermal runaway in a lithium-ion battery is both flammable and toxic. 217. The fire energy content, electrical and chemical, of cobalt oxide cells is about 100 to 150 kJ a times H, most of it chemical. 218. Around 2010, large lithium-ion batteries were introduced in place of other chemistries to power systems on some aircraft. As of January 2014, there had been at least 4 serious lithium-ion battery fires, or smoke, on the Boeing 787 passenger aircraft, introduced in 2011, which did not cause crashes but had the potential to do so. 219. 220. UPS Airlines Flight 6 crashed in Dubai after its payload of batteries spontaneously ignited. To reduce fire hazards, research projects are intended to develop non-flammable electrolytes. Damaging and overloading. If a lithium-ion battery is damaged, crushed, or is subjected to a higher electrical load without having overcharge protection, then problems may arise. External short circuit can trigger a battery explosion. 221. If overheated or overcharged, lithium-ion batteries may suffer thermal runaway and cell rupture. 222. 223. During thermal runaway, internal degradation and oxidization processes can keep cell temperatures above 500 degrees Celsius, with the possibility of igniting secondary combustibles, as well as leading to leakage, explosion or fire in extreme cases. 224. To reduce these risks, many lithium-ion cells and battery packs contain fail-safe circuitry that disconnects the battery when its voltage is outside safe range of 4.2 V per cell, 64, 78, or when overcharged or discharged. Lithium battery packs, whether constructed by a vendor or the end user, without effective battery management circuits are susceptible to these issues. Poorly designed or implemented battery management circuits also may cause problems. It is difficult to be certain that any particular battery management circuitry is properly implemented. Voltage limits. Lithium-ion cells are susceptible to stress by voltage ranges outside of safe ones between 2.5 and 3.65/4.1/4.2 or 4.35 V, depending on the components of the cell. Exceeding this voltage range results in premature aging and in safety risks due to 3 active components in the cells. 225. When stored for long periods, the small current draw of the protection circuitry may drain the battery below its shut-off voltage. Normal chargers may then be useless since the battery management system, BMS, may retain a record of this battery or charger failure. Many types of lithium-ion cells cannot be charged safely below 0 degrees C, 226, as this can result in plating of lithium on the anode of the cell, which may cause complications such as internal short-circuit paths. Other safety features are required in each cell. Smiley 64, shutdown separator, for overheating. Tearaway tab, for internal pressure relief. Vent, pressure relief in case of severe outgassing. Thermal interrupt, overcurrent /overcharging /environmental exposure. These features are required because the negative electrode produces heat during use, while the positive electrode may produce oxygen. However, these additional devices occupy space inside the cells, add points of failure, and may irreversibly disable the cell when activated. Further, these features increase costs compared to nickel metal hydride batteries, which require only a hydrogen/oxygen recombination device and a backup pressure valve. 78. Contaminants inside the cells can defeat these safety devices. Also, these features cannot be applied to all kinds of cells. For example, prismatic high-current cells cannot be equipped with a vent or thermal interrupt. High-current cells must not produce excessive heat or oxygen, lest there be failure, possibly violent. Instead, they must be equipped with internal thermal fuses which act before the anode and cathode reach their thermal limits. Replacing the lithium cobalt oxide positive electrode material in lithium-ion batteries with a lithium metal phosphate such as lithium-iron phosphate, LFP, improves cycle counts, shelf life and safety, but lowers capacity. As of 2006, these safer lithium-ion batteries were mainly used in electric cars and other large-capacity battery applications, where safety is critical. 227 recalls. In 2006, approximately 10 million Sony batteries used in Dell, Sony, Apple, Lenovo, Panasonic, Toshiba, Hitachi, Fujitsu and Sharp laptops were recalled. The batteries were found to be susceptible to internal contamination by metal particles during manufacture. Under some circumstances, these particles could pierce the separator, causing a dangerous short circuit. 228. Japan Airlines Boeing 787 lithium cobalt oxide battery that caught fire in 2013 transport class 9 lithium batteries. IATA estimates that over a billion lithium metal and lithium-ion cells are flown each year. 218. Some kinds of lithium batteries may be prohibited aboard aircraft because of the fire hazard. 229. 230. Some postal administrations restrict air shipping, including EMS, of lithium and lithium-ion batteries, either separately or installed in equipment. Non-flammable electrolyte. In 2023, most commercial Li-ion batteries employed alkyl carbonate solvent, S, to assure the formation solid electrolyte interface on the negative electrode. Since such solvents are readily flammable, there has been active research to replace them with non-flammable solvents or to add fire suppressants. Another source of hazard is hexafluorophosphate anion, which is needed to positivate the negative current collector made of aluminium. Hexafluorophosphate reacts with water and releases volatile and toxic hydrogen fluoride. Efforts to replace hexafluorophosphate have been less successful. Supply chain. The electric vehicle supply chain comprises the mining and refining of raw materials and the manufacturing processes that produce lithium-ion batteries and other components for electric vehicles. The lithium-ion battery supply chain is a major component of the overall EV supply chain, and the battery accounts for 30% to 40% of the value of the vehicle. 231. Lithium, cobalt, graphite, nickel, and manganese are all critical minerals that are necessary for electric vehicle batteries. 232. There is rapidly growing demand for these materials because of growth in the electric vehicle market, which is driven largely by the proposed transition to renewable energy. Securing the supply chain for these materials is a major world economic issue. 233. Recycling and advancement in battery technology are proposed strategies to reduce demand for raw materials. Supply chain issues could create bottlenecks, increase costs of EVs and slow their uptake. 231. 234. The battery supply chain faces many challenges. Battery minerals typically travel 50,000 miles from where they are extracted to downstream manufacturing facilities. Deposits of critical minerals are concentrated in a small number of countries, mostly in the global south. Mining these deposits presents dangers to nearby communities because of weak regulation, corruption, and environmental degradation. These communities face human rights violations, environmental justice issues, problems with child labor, and potentially generational legacies of contamination from mining activities. Manufacture of battery technology is largely dominated by China. Environmental impact. Extraction of lithium, nickel, and cobalt, manufacture of solvents, and mining byproducts present significant environmental and health hazards. 235, 236, 237. Lithium extraction can be fatal to aquatic life due to water pollution. 238. It is known to cause surface water contamination, drinking water contamination, respiratory problems, ecosystem degradation and landscape damage. 235. It also leads to unsustainable water consumption in arid regions, 1.9 million liters per ton of lithium. 235. Massive byproduct generation of lithium extraction also presents unsolved problems, such as large amounts of magnesium and lime waste. 239. Lithium mining takes place in North and South America, Asia, South Africa, Australia, and China. 240. Cobalt for Li-ion batteries is largely mined in the Congo. See also mining industry of the Democratic Republic of the Congo. Manufacturing a kilogram of Li-ion battery takes about 67 megajoule, MJ, of energy. 241. 242. The global warming potential of lithium-ion batteries manufacturing strongly depends on the energy source used in mining and manufacturing operations, and is difficult to estimate. But one 2019 study estimated 73 kilograms CO2e/kilowatt-hour. 243. Effective recycling can reduce the carbon footprint of the production significantly. 244. Solid waste and recycling. Li-ion battery elements including iron, copper, nickel and cobalt are considered safe for incinerators and landfills. 245. These metals can be recycled. 246. 247. Usually by burning away the other materials. 248. But mining generally remains cheaper. Recycling winking sad smiley. 249. Recycling may cost $3/kilogram, 250, and in 2019 less than 5% of lithium-ion batteries were being recycled. 251. Since 2018, the recycling yield was increased significantly, and recovering lithium, manganese, aluminum, the organic solvents of the electrolyte, and graphite is possible at industrial scales. 252. The most expensive metal involved in the construction of the cell is cobalt. Lithium is less expensive than other metals used and is rarely recycled. 248. But recycling can't prevent a future shortage. 246. Accumulation of battery waste presents technical challenges and health hazards. 253. Since the environmental impact of electric cars is heavily affected by the production of lithium-ion batteries, the development of efficient ways to repurpose waste is crucial. 251. Recycling is a multi-step process, starting with the storage of batteries before disposal, followed by manual testing, disassembling, and finally the chemical separation of battery components. Reuse of the battery is preferred over complete recycling as there is less embodied energy in the process. As these batteries are a lot more reactive than classical vehicle waste like tire rubber, there are significant risks to stockpiling used batteries. 254. Pyrometallurgical recovery. The pyrometallurgical method uses a high-temperature furnace to reduce the components of the metal oxides in the battery to an alloy of Co, Cu, Fe, and Ni. This is the most common and commercially established method of recycling and can be combined with other similar batteries to increase smelting efficiency and improve thermodynamics. The metal current collectors aid the smelting process, allowing whole cells or modules to be melted at once.